all, I'd like to thank Rock for the nice introduction and for the invitation. It's a huge pleasure for me to be here talking a little bit about one of my favorite subjects in mathematics. This talk was intended to be for high schoolers, but we have a lot of mathematicians here. I'll try to keep it simple. So the first half is gonna be about the concept of infinity and how we define it in mathematics. The second part is gonna be a little bit more philosophical, so we'll come to that a little bit later. So if something is not clear at any point, just feel free to interrupt me, and I'll be happy to try to clear things up. So infinity, that's a huge word, right? And from a very, very young age, we all start pondering about the existence of infinite things, right? So when we are asked as kids, which is the largest number, well, we say the largest number that we know, right? 100. And then our parents say, well, it's not, it's 101. Okay, then it's 1,000. No, it's 1,001. And so from the very beginning, we start seeing that there's something that doesn't have an ending, right? So, and things like the universe also come into play, and we start looking at the stars and think about them as infinite, as an infinite number. So this is actually an open question. If the universe is infinite or finite, we don't know. But you see that's from a very young age, we start looking at something else, something like massive. So how can we define infinity and infinite stuff? So we have to keep in mind that it's something like endless, right? And well, it turns out that if we go back to history, Aristotle distinguished two types of infinity, one of which is the potential infinity, which essentially is the never-ending process, right? So we have 1 plus 1 plus 1 plus 1. This is never-ending, and this is what he called potential infinity. And he distinguished it from the actual infinity, which is the real infinity. So we see objects as real entities, right? Real objects. And he postulated that the actual infinity is impossible. So it doesn't exist. It's just some sort of imagination that we have. And the Greeks were kind of like afraid of the concept of infinity. But even though Euclid proved that there are infinitely many prime numbers, where a prime number, well, probably here we all know what a prime number is. So it's just a number that cannot be, that can be divided only by 1 and themselves. So, and minus 1 and minus themselves. But Euclid avoided the word infinity because, of course, they were afraid. And arguably, one of the most famous paradoxes regarding or relating infinity is Zeno's paradox. And let me tell you what this is. So essentially, Achilles, who was believed to be the strongest and fiercest warrior in the Greek army, right? So he wanted to raise a tortoise. So the tortoise, okay, they decided to raise. But Achilles, because he was so strong, he gave the tortoise an advantage of 100 meters, right? So 100 meters over Achilles, the tortoise will start at some point, and Achilles will start behind. So given a finite amount of time, well, Achilles will reach the point, the position of the tortoise, but the tortoise will be ahead of Achilles. And after the second finite amount of time, Achilles will reach the second position of the tortoise, and the tortoise will be ahead of Achilles. So the paradox is that Achilles never reaches the tortoise, right? And this is sort of puzzling, right? This is paradoxical. But if we put it in mathematical terms, well, if we denote A as Achilles' speed in meters per second, and X is the tortoise's speed, then Achilles needs 100 over 8 seconds to reach the initial position of the tortoise. then he needs 100 over 8 times x divided by a, right? Seconds to reach the second position. And we keep going like this over and over. And you as mathematicians realize, well, this is just a geometric series. And we know how to compute this number here, because x over a, there's going to be smaller than 1. So this is actually a finite number. So it's well defined. So there's no paradox in here. But this illustrates how mathematical formalism can help us understand paradoxes in a better way. And we don't have to go this far. If you try to express 1 over 3 as a decimal, well, you'll come to the realization that, well, you need an infinite amount of time to do this, right? Because you start dividing and then you get 0.3, then 3, then 3, then 3, then 3, and you go on forever. So there is actually a concept of infinity happening all over the place, okay? So let me tell you just a little bit of history. I like history, so, because we can see how facts were going. And so European mathematicians in the 17th century started using the infinity as in a systematic way. So for instance, with the introduction of calculus, Newton and Leibniz treated very small quantities, right? So infinitesimal. And then John Wallis introduced the concept, the symbol of the lemniscate. And this is the symbol of infinity that we know today, that we use widely. And even the great mathematician Leonhard Euler devised the importance of infinity using the sums and products. So he manipulated products and sums, infinite products and sums, in a very natural way, right? So he looked at infinity like a different object. And he didn't even have a proper definition of convergence or infinity, okay? So, well, mathematicians gave a very, very huge step forward with the development of calculus by Cauchy and Bolzano. And, they defined what a limit is, what convergency is. So, as this epsilon delta definition that we all love, right? And, okay, so after the history, I'm going to tell you how we define infinity. So intuitively, the set of natural numbers is infinite, right? There's no doubt about it. But how do we define this? Well, we do this in terms of functions, right? So let's say that we have a couple of chairs, right? Like these chairs somewhere over here, and that we have some students, right? Here. So how can we assign a chair to each student, right? Well, this is simple. We just select one chair and we just assign, right? And this is in a unique way. So we can do the same with 1, 2, 3, 4, and 5, right? We're just assigning numbers to chairs. So we're identifying objects with numbers, right? And this is in a unique way. So this correspondence is what will help us to understand how to define infinity. So counting is just a mere one-to-one correspondence between two sets, right? And this one-to-one correspondence, we call it bijection. And this was first introduced by Cantor and studied by Cantor, who first systematically studied set theory and introduced all the formalities needed to develop set theory and the theory of infinities. And here's the formal definition. So we say that the set is finite if and only if there's a natural number such that we can biject our set X into an initial segment of the natural numbers, right? So we have from 0 to n, and then we can find a bijection. So a one-to-one correspondence. Nothing fancy so far, right? And well, if such bijection doesn't exist, then we call the set infinite. So this is a very interesting definition, right? Because we only need the natural numbers, and then we know when a set is infinite or finite. And of course, we have examples of infinite sets, such as the natural numbers, the real numbers, the complex numbers. And well, we say that two sets have the same size if and only if there's a bijection between them, right? And we define this x smaller than y if and only if there's only an injection. So it means a one-to-one correspondence that cannot cover the whole range or the set. Okay, so now we know, and probably here, and this from everyone knew these definitions, but we'll come to the first big result, which is about countable and uncountable sets, right? So we consider the set of infinite binary strings or sequences, right? So zeros and ones. We have bits. So for instance, this infinite sequence is part of our set. And then we can see that this set contains a copy of n, right? Just put the first bit 1, the second element will be 2 ones, then 3 ones, and so on. Then you have a copy of the natural numbers. Okay, so this set is infinite. And I claim that there's no bijective function between n and 0, 1 to the n. How do we do that? Well, imagine that you have such a bijection. So this one-to-one correspondence. Then we can enumerate the sets of 0, 1 to the n like this. So the first element is going to be A0, 1, 2, A3, and so on and so forth. And we just define a new binary, infinite binary sequence, A infinity, that differs exactly at one position, at the ith position from AI. Okay? So this A infinity is an element here, but it's different from all the elements in the list. Okay? So this enumeration is impossible. So this cannot happen. And this is called the diagonal Cantor's argument. And you see, so we start with an enumeration, and then we found something that is not there. Therefore, what we actually proved is that these are different infinities. Okay? So we know this. If we denote with aleph naught the cardinality of the natural numbers in 0, 1 to the n, the cardinality of 2 to the, the cardinality of this thing with 2 to the aleph 0, then aleph 0, aleph naught is smaller than 2 to the aleph naught. So we proved this, okay? So far, so good. We have two infinities. Well, nothing special, but we can continue like this, and then we can create an infinite list of infinities, right? So this is interesting, right? By powering, we just have so many infinites. So I will let you contemplate this result for a second. And well, so now we know that there are infinitely many infinites. Some of them can be enumerated using alephs. So we have 0, 1, 2, 3, 4, 5, 2, 2, 2 till the end. Well, there's no end, right? And then we have aleph 0, then aleph 1, aleph 2, aleph 3, and they continue like this, all the alephs. And so we have some of these, we call them cardinal numbers. And we can perform arithmetic like in the usual finite setting. So if we have two cardinal numbers, then we can add them. And this addition behaves nicely, right? So it's commutative, it's associative. We have an identity, the zero is an identity. And weird things happen. So if you consider, for instance, the sum of two alephs, then it's going to be just the maximum of both, right? So if you have aleph 0 and aleph 1, well, the sum is going to be aleph 1, right? So you see that in the infinite realm, weird things happen. So the same happens for multiplication. Okay, so this is about cardinal arithmetic. So you see that it's sometimes counterintuitive. Like the properties are not so easy, like in the final realm. And one of the first results, or at least first statements, relating those cardinals was the continuum hypothesis. And if we denote so the real numbers with R, this R, then the cardinality is going to be 2 to the Aleph 0. We can prove that. And then the continuum hypothesis or Cantor's problem is that is it true that for every infinite subset of the real numbers, so either it has the size of the natural numbers or the size of the real numbers, right? So we have this dichotomy. And well, Cantor spent a lot of time trying to prove this statement, and we'll come to it a little bit later at the end, towards the end of the talk. But first, let me tell you another interesting paradoxical result of the infinite. And for this, I'll need to define something. Now, imagine that we have shoes. So an infinite list of shoes, okay? So now we have a lot of shoes. So how can you select exactly one shoe from each pair? Well, you can say, well, I'll choose the left shoe. And the second, well, I'll select the left shoe. And then the left shoe. Okay, so from each pair, you're selecting the left shoe. Perfect. So this is a well-determined, we call it choice function. Because, I mean, even though this list is infinite, you can tell me exactly which shoe you're taking. But if you think about socks, well, socks, you have a pair of socks, right? With maybe Christmas socks, because, you know, the season. And they are indistinguishable. And you have an infinite list, again. So how can you select exactly one sock from each pair? So which sock will you select? Well, you can tell me left, but which one is left, we don't know. There's not any distinction between them, right? So actually, there's no an easy way to select these exactly one sock from each pair, right? So there's not a choice function. And actually, we need to state it as an axiom. So this is called the axiom of choice. And the axiom of choice is that for every collection of non-empty sets, there's a choice function. So one function that selects exactly one item from each set. Okay? And in the beginning, this axiom was controversial due to its non-constructive nature. And we'll see one example, one instance of these paradoxical results that it produces. And the problem is, okay, I'll tell you the problem later. But first, let me tell you that nowadays, mathematicians use it freely. And I mean, and I'll also tell you why later. So let me tell you about the Banach-Tarski paradox. Imagine a sphere, okay? Have you imagined a sphere already? Yeah? If not, I hope you imagined like this. So we have a sphere. And now consider rotations over the x-axis and the z-axis, okay? So rotations of this degree, degrees, right? 70.53, exactly that. So if you have a point here, so A is going to be rotation over the x-axis. And what's B over the z-axis? So we have our point P, and if we rotate on the z-axis, P will move somewhere here, and we rotate again, it will move there. And if we rotate up now with A, so now we're rotating with the x-axis, it will move. And then we can do the same. Now, B minus 1 on the other direction. And so you see that we have a bunch of rotations here, okay? And you see that 1, 0, 0 maps to this thing here. Something very not similar to 1, 0, 0, right? And what we can prove is that 1, 0, 0 is never reached back under these rotations, okay? So what we are actually saying here is that these rotations are essentially words in A and B, right? So you have a word A and then A, then B, then A, B minus 1, then B, B minus 1, B minus 1, A, and stuff like that. So this is just all the possible words that you can form with 2 letters, okay? So this is codifies the rotation. And why are these helpful? Well, collect all such rotations. So I don't have to talk in code here. I mean, this is a group, right? So we have a group. And then what we do, well, we consider the action of the group, and then we partition with the orbits, right? And then, so these orbits form a partition of the sphere. And so we have just cut the sphere in a bunch of things, a bunch of pieces. Okay, so now select exactly 1 point from each partition, from each orbit, okay? So then using this selection, we can prove that there's another partition, P1, P2, P3, P4, such that if we rotate P2, we obtain P2 union P3 union P4. If we rotate P3, we have P1, P2, P3. So this is just another partition of the sphere. But magic happened, right? Because if you're careful, you notice here that you just rotated one piece. And if you add P1 here, then you have the whole sphere. And if you add P4 here, you have the whole sphere, right? So what we are doing, if we reassemble, then actually from one sphere, solid sphere, we created 2 spheres magically, right? So you see, if we apply the same procedure finitely many times, then we can start from a P and create the sun, right? So this is sort of paradoxical, isn't it? And that's why the axiom of choice was frowned upon, right? Because, well, this is not possible, right? How can you start from a sphere and create 2 spheres? Well, and the reality is that this is not so paradoxical. I mean, this is just a theorem, and the problem or the idea behind is that there's a non-constructive nature in the proof. So we cannot partition the sphere nicely. So we don't know how to do it properly. So it's just a mess. Okay, so we don't have a specific way to partition the sphere to get 2 spheres. And moreover, those pieces, we cannot assign a notion of volume to those pieces. Okay, so this is why we can do it. And well, this is like the bottom line of this part is that at the end of the day, it's your choice to choose choice or not to choose choice. Okay. Okay, so that's about the axiom of choice. Now, the second part will touch upon a little bit of philosophy, so bear with me. And near the end of the 19th century, there was a series of paradoxical results, and this led to foundational crisis in mathematics. And simple things like, how do we formally construct the natural numbers? Or even things like, well, what's a set? Started puzzling mathematicians, philosophers, and people in general. And Russell came up with the following paradox. So if you consider a set R of elements that do not belong to themselves, so that's it, you consider X in R if and only if X is not in R, does R belong to R? That's the question. Well, you can say it's obviously true, right? Well, if R belongs to R, then by definition, R doesn't belong to R, so R doesn't belong to R. This is a contradiction. And then you say, well, it follows that. Yes, if R doesn't belong to R, then by definition of R, R belongs to R, and this is again a contradiction. So what's the conclusion? That this set R cannot exist. And so this actually puts a lot of restrictions of what we can call a set. Things like this cannot be a set. And these types of paradoxes led to a strong opposition to counter set theory and a reevaluation of the foundations of mathematics and the logical basis of math was needed. And different philosophies were brought about, and between them, different schools of philosophical schools of thought, and such as constructivism, infinitism, formalism, logicism, and Platonism. So here we have a Brouwer, and he was the leader, let's say, of the constructivist part and the main opposer of Cantor. And I will tell you a little bit about just the formal part, which is the most interesting, at least for me. And what's the formal part is that, well, David Hilbert, maybe all of the people in this room have heard of Hilbert, proposed to formalize all mathematics using an axiomatic framework, right? So using a precise formal language and a nice set of axioms in such a way that all mathematics can be done here in a complete way, meaning that all truths can be proved and that it's consistent, that there are no contradictions in our system. And to understand this a little bit, just let me elaborate on what I mean with the axiomatic setting. And all modern mathematics follow the deductive method, right? So we prove things using certain axioms or things that we already know. We deduce results to prove things about our objects. And this is not new. This goes back to Euclid and in his treatise of geometry, of Euclidean geometry that we call now. And this is the elements, right? So he started with a set of axioms and started proving things about planar geometry. So there was a very controversial postulate, which is the fifth postulate or the parallel postulate, and essentially says that in a plane, if you draw a line and a point which is not on the line, then there's exactly one parallel line to this point, right? So this, everyone seemed to be happy with that, and they said, well, this is obvious, but people tried to prove it using the other four axioms, and they were unsuccessful. So why is this the case? Well, there are two forms of negation of this axiom. So the first one, how do you negate the postulate parallel? The parallel postulate is that there's at least two lines parallel to your initial line, and then this yields hyperbolic geometry. Okay, where, for instance, properties like here we have a triangle where the inner angles do not add up to 180, but something smaller, right? And Lobachevsky was the first one to study hyperbolic geometry. And if you negate the parallel postulate as if there are no lines parallel to the initial one, then you get elliptic geometry or spherical geometry, right? Where you can have triangles whose inner angles add up to something larger than 180. So these are types of geometries that obey all postulates of Euclidean geometry, except for the fifth postulate, right? So these geometries tell us that the parallel postulate is independent from the set of axioms, from the rest of the axioms, because we have models where all the truths about geometry can be proved, but this parallel postulate is not true, okay? So this is the idea. You can think of it in field theory. I mean, fields, groups, arithmetic, you have Peano's axioms, you have the theory of fields, right? You have a set of axioms, you have vector spaces also, groups, and so on and so forth. And about truth, so in the theory of fields, if you think about the statement, there exists an x, such that x squared plus 1 is 0. Well, is this true or false? It depends where you interpret this statement, right? It is true in the complex numbers, but it's not true in the real numbers, for instance. So it really depends how you assign values to your variables. And something similar happens with set theory. And all of these ideas led to the development of the axiomatic set theory, which is now called Zermelo-Fraenkel. So these are the ZF axioms, where virtually all mathematics take place. So if you're doing analysis, combinatorics, graph theory, whatever, we can plug it here. And in principle, all things that you're proving are based on Zermelo-Fraenkel. And it then functions as a solid basis of mathematics, right? So Hilbert's program was successful. And here we have Hilbert, right? But he doesn't seem so happy in this picture. And we'll see why. So it turns out that our friend Gödel proved that if you have a consistent theory whose set of axioms is nice, and this is strong enough to carry out basic mathematics, arithmetic, then this theory has to be incomplete, right? So that means under these assumptions, there are statements that cannot be proved nor or disproved. So there are independent statements. There are things that you cannot prove. Well, we can live with that, right? It's not a big deal. And then Gödel also proved in the second incompleteness theorem that under the same assumptions, the theory cannot prove its own consistency. So rephrasing, we cannot even prove that our theory is consistent. So this is a little bit more serious, right? Because we don't know if what we're doing is actually correct. And he does seem happy, right? Unlike Hilbert, a little bit. So Hilbert's program was doomed to fail due to Gödel's results. And so you have to summarize in an axiomatic framework, we have to live with the fact that there will be things that we cannot prove at all. And we cannot even prove that our theory is consistent. If you want something strong enough as arithmetic, like piano, or even weaker theories. But the good thing is that not everything is lost. Because, well, most working mathematicians do not have to worry about these subtleties. And another important reason why we don't have to worry that much is that we have relative consistency proofs. So we just assume that ZF is consistent, for instance, and then we can see if we add something else, like if you remember Euclidean geometry, we added the parallel postulate, and this is consistent because, well, we have a model of it, and you can just negate it, and then this is consistent. So all the things that you can prove there won't lead to a contradiction. So we can do the same for set theory. And going back to our initial question, so you remember Cantor's problem about the cardinality of subsets of real numbers. Well, first thing, Gödel proved that the axiom of choice is consistent. So we can use it. So you don't have to worry. If you use it, everything will be fine, right? And he also proved that the continuum hypothesis is consistent as well. So we can use it as well. So this is great. Whatever you can deduce from CH and ZF will be consistent, okay? Assuming that ZF is consistent. But a breakthrough work, a pioneering work of Paul Cohen showed in 1963 that the negation of the axiom of choice is also consistent. So it's your choice to use it. You can use it freely. I mean, if you use it or not, you'll have a consistent theory, assuming that your initial theory is consistent, right? So you can use it. That's good. But he also proved that the negation of the continuum hypothesis is consistent. So you cannot prove either the axiom of choice of the continuum hypothesis using ZF, right? And unfortunately, our good friend Cantor died trying to prove something that it was impossible to prove or to refute, right? So that's a shame, but at least his legacy will stay forever. And here we have a picture of older Cantor. And just I'll finish with this quote. And I think I had a lot of time. And that the essence of mathematics lies precisely in its freedom. And that's all I wanted to tell you today. Thank you very much.